Our first presenter is Nick Silikas, and from the University of Manchester. You can stand up and grab your microphone. And the title of his presentation is The Effect of Filler Size and Shape on Mechanical Surface and Handling Properties of Resin Composites. Thank you very much.
Right. Okay, well, good morning, everybody. I would like to thank Paulo Cesar for organizing this one and inviting me along with everybody else and creating this such a superb panel of experts, and namely the people that will follow me. But so when Paulo initially invited me, I asked him, "What do you want me to talk about?" So he said, "Just give us an overview of aspects of your lab, some of the research you're doing there, some of the recent research that you're doing, and some of your philosophy." Or I think he mentioned philosophy in any way. So I took it at his face value that he mentioned philosophy. So I have as a running title. I'm just trying to switch this on. There it's on now. So as I was saying, I was talking to Paulo. He was explaining me what he would like me to present. So like a week ago, I came up with this running title. So I'll try to talk a bit about resin composites, philosophy, and honey. So, now, as I said, I'm going to talk about three things. First of all, the lab, I work, my research, and a bit about my philosophy as well. So the first thing, the lab, and a bit about me as well. I've been in Manchester for many years. I did my studies there, and I worked there in the school, in the dental school, for at least 12, 13 years now. But I don't originally come from Manchester or UK. So that's me on here, in very close to my hometown. This is my young goddaughter. It was a few years ago. So as you can possibly all guess, this is a typical photo from Greece, which is my original place and my hometown. But going back to the University of Manchester, it's a very research-intensive university, and the dental school is ranked #1 in the UK on top of all the other UK dental schools. That is from an independent assessment panel that goes through the procedure every 4 or 5 years to assess all the schools, all the universities, and all the departments. So at the moment, we're #1. That's why we're promoting it. It might change. A bit about the lab. You can see my colleague there. It's Professor David Watts. On the back, some of the admin staff. This is some of the postgraduates that we have at the moment. Some people you might recognize as well. Again, another photo from us in the lab. This is from the European Dental Materials meeting that we held in Manchester a couple of years ago. So you might recognize some guys like Professor Van Noort, this is Brian Darvell, Charles Lloyd, Gary Fleming, quite influential in the UK dental materials community. You might know her. And you might know these people as well, doing some more research in the lab there. Okay, now, Paulo also asked me to provide, and the other speakers, a short biography, which I did. Now, if any of you read it and managed to stay all the way to the end, at the very last line, I put down 3 interests. So my 3 interests are basketball, is the first one here. I've always been involved in playing basketball. Nowadays, my playing time is diminishing and my coaching time is increasing. So this is from coaching a women's team and winning the National League in England. So this is the trophy we were awarded. One of the other things, and not by any means the last one, is caipirinha. So this is me on my summer holidays, and this is my goddaughter that grew up from that initial photo, so it's a bit older now. But I'm still enjoying the caipirinha there. And the last thing that I put down in interest is football, and we're happy in Manchester to have the best team in the world, being the richest team in the world. And obviously I'm talking about Manchester City, just to clarify. Okay. And that's me in a very recent game. That's in a Champions League game that took place about a couple of weeks ago. Watching the game there. So that's me from Manchester in the lab. Now, some aspects of my philosophy and philosophy of research. I'd start with being skeptic. And allow me here to deviate a bit and going to the etymology of the word skeptic and being skeptical, which has a Greek origin, and the skep, this is the Greek version of skep, means to guard. That was the original meaning of the word, and it was used, the person who is the guard as well had the same name. And these people were in a high tower, and they were guarding everything, and they're obviously as a guard, they were supposed to examine the whole area. So that's how the original meaning came, and that's how the word then evolved. And it means someone who is examining everything in front of him. And in order to be a good guard, you have to be able to assess what you see in front of you and be able to make a good decision and see if that is real, if that is a danger, and so on. And then, finally, oops, I'm moving too fast. It's a bit sensitive. Finally, the word means if you examine too much, then you will start expressing some doubts. And I have a quote by Feynman, who is one of my favorite physicists and is a very eminent physicist and researcher of the 20th century, who he said, as long as it's possible, we should disregard authority, especially whenever the observations disagree with it. So if you're going to remember one thing from my lecture, then remember this one. You must doubt the experts if you want to move on in research. Okay, so a bit more about research, now moving more towards resin composites. We have this part of philosophy, let's say, in the school there. There is a life cycle in dental biomaterials and especially in the resin composites. So at the very beginning, before you even use any material, there's the storage properties, and there's a question of selecting the right material for the right application and the right patient. Before you place it, the material has certain properties like mixing, the viscosity, the working time of the material, and how well it can adapt to the cavity. Then during placement, you have properties like the setting time, and you have dimensional and thermal changes taking place. And finally, after you place it there, you want that material to stay as long as possible and to maintain its function and role. So you have medium-term properties, which can be mechanical and physical, and longer-term properties. You can have wear, can take place after 3 years, fatigue properties, and so on. So there is a timeline, and at any point you can examine the properties of that material. That is not going to give you, if you examine one property, it's not going to give you the whole picture, but it will tell you something about the specific time and the specific property of that material. So a bit about the research. I'm going to talk about resin composites and mainly about nanocomposites. So I'm starting with a couple of slides which probably are familiar to most of you. So when we're talking about nanometer size, we're talking about very, very small fillers. So this is what a micron particle looks like, and then when you have something at 20 nanometer, this is how small it is compared to a micron, which is very small anyway. As an analogy, you have a meter 10 to the 9 nanometers. So if you have the Earth, and this is a football ball, that is the analogy between a meter and 1 nanometer. It's an Earth and the actual football ball, just to give you a more size what we're talking about. Now, nanotechnology, nanoscience, has been around for a few years, and possibly the term nanotechnology was mentioned about at least 50 years ago, and it was coined by Richard Feynman that I quoted before back in the 60s. So he was the first one who described nanotechnology, and he very famously said that there's plenty of room in the bottom. This is some more recent quotes. They are from the Journal of Materials Chemistry in 2005, talking about nanoscience and biomimetics as the thing to move forward. And dental materials and dentistry, they're trying to move into that direction. They're trying to incorporate some of the technology that's been around to improve the performance of the materials. So the properties I'm going to talk about, I'm going to mention some mechanical properties like Young's modulus, bulk modulus, some optical properties, which can be the surface roughness, gloss, and color, and finally some handling properties like packing and viscosity. So going back to the timeline that I was using before, I'm just picking certain properties during that timeline, and I'm actually reversing the timeline. So instead of going to the handling first, I'm going to the mechanical, which is more medium long-term properties, and the optical properties, and then finally the handling. Now, all of this research that I'm going to describe is done by using what we would call model composite materials. So these are experimental formulations that were formulated with a specific purpose, namely to know exactly what is in there so we can very systematically hit one parameter and we can study that parameter alone. So these ones, they were divided as spherical filler particles and irregular filler particles. The difference is that you can have different filler sizes, and you can have unimodal or multimodal approaches in there. They all have the same resin matrix, and they all have the same filler volume. So filler volume was about 56.4%, and in terms of weight, it roughly translates to about 72 for most of them there. This is what they look like. We took some SEM of those composites. This is one with a bimodal approach, and it has micron filler and some nanofillers at about 100 nanometers. This is one with just 1 micron. It's coming again. And this is a close-up with that 1 micron filler distribution. And this is the same one with the resin matrix as well in there. So as I said, especially in the last decade, manufacturers are trying to put new materials into the market. And there were some changes in the resin matrix, so I'm not going to go at all into them. But one of the most significant changes was about fillers, the size of the fillers and the filler volume. The idea is that by having nano fillers, hopefully we can enhance the aesthetic and mechanical properties of our material. So in my first part of research, I'm going to focus on the Young's modulus as a property that we studied there. So in this research, we wanted to measure the Young's modulus of a series of these model polymeric materials. And the two parameters that we investigated was the filler size and the filler shape. So our first 9.5 hypothesis was that filler size and shape would not affect it. And the second one, there's no difference between the two measurement methods that we used. So in this one, the two methods that we had, the first one was compression load, and the second one was nano indentation. In total, there were 12 formulations, and these are the formulations. You remember the big table, this is the one used for that one. This is the details of the specimens. This is for the Young's modulus, so some rod cylindrical specimens. They were placed there on a universal testing machine. They were free to expand, and they were loaded with a gradual load up to 1,000 newtons. This is the raw trace that we got, the strain stress curve, and by looking at this part here, we were able to determine the Young's modulus of those materials. Also, we prepared some different specimens for nano indentation. So these were like disc-shaped specimens. For nano indentation, you have to have a very smooth, flat surface. So this was metallographically polished to obtain that surface. This is what they look like. So you have this, you bend it into polystyrene rings, and then they go into the nano indenter. This is the nano indenter that we use, an MTS one. This is the specific specifications of the nano indenter, diamond tip, 100 nanometer radius, and the load is 50 nanonewtons. So that's why we're talking about nano indentation. So the loads are very, very small. And we used the continuous stiffness measurement technique to determine the stiffness of the samples. This is the trace that you get from nano indentation. So you get the loading segment, then you have the peak holding time, and then the unloading. And from that trace, you were able to calculate your stiffness, which is the Young's modulus of the material.